right, so up to this point, we have mostly been considering individual charges and what their overall behavior is. But we have looked at a couple of cases where we have both positive and negative charges present. And I'd like to focus on that for this video. So let's imagine that we have a positive charge and a negative charge that are connected by a rigid rod. Okay, so that may seem like kind of a weird situation, but this actually, conceptually at least, shows up in a lot of places and has a lot of practical applications. Okay, so in particular, I want to consider the case where these two charges are equal and opposite. So overall, the net charge here is 0. Okay, so we have this neutral object, but it still has some positive and negative charges present. Okay, so we call this object a dipole because it has two poles. So an old-fashioned word for charge was pole. We still use that in the case of magnets, which we'll study later on, but this is sort of a holdover from a previous time. So we have two poles, a positive pole and a negative pole, and that's why we call it that. Interestingly, there are also cases where we can have more than two, so quadrupoles or sextupoles and so on exist, and they are exactly what they sound like. You have an arrangement of multiple charges and study the overall behavior of that structure. Okay, so the reason that this is interesting is because this thing is overall charge neutral, but it still has electrical interactions. Of course, you have seen that before. One example was the polarization of a pith ball. So that was a neutral object that had an electrical interaction because it became polarized. Well, here we're considering an object that's permanently polarized. So we have this permanent dipole. You might wonder what would be a real-life example of this. So it turns out lots of molecules actually do this. They have this structure. Oh, goodness. Okay. So, for example, water has an oxygen and two hydrogens, arranged sort of like this. And we don't have the rigid poles connecting them, of course, but the structure is still fixed by chemistry. Okay, and so it turns out that the oxygen is better at holding on to electrons than the hydrogen. Or you can think of it that the electrons spend more time near the oxygen. Okay, so we end up with a slight positive charge near the hydrogens and a negative charge near the oxygens. It's not a complete polarization or not a complete ionization. We don't have a hydrogen ion and an oxygen ion, but it is still true that the electrons disproportionately spend time near the oxygen. And so we get a permanent dipole in this case. So in situations like this, we call this a polar molecule. Okay, and a lot of the properties of water can actually be understood in terms of that polarity. Okay. There are also lots of other biological materials that take advantage of molecular polarity. So for instance, amino acids stick together because they have a positive side and a negative side, and so that's how they make these chains. Nucleotides also do the same thing. They're able to kind of zipper together because they have polar regions near the interaction spots, and so you get a positive on one side and a negative on the other, and those want to stick together. Okay, so this is something that is very practical in terms of biological materials. Okay, so what I want to consider then, back to our more ideal dipole, is how does that dipole interact? What sorts of behaviors does it undergo? So first, let's consider the force on a dipole in an electric field. Okay, and just to make this simple, I'm going to have a constant electric field. Electric field lines going to the right, like so. Okay, and I'm going to represent the dipole in a different color. So let's say I have the positive charge over here and the negative charge over here, and then there's some distance apart, d. Okay. Well, if I want to consider the force on these, well, the force will just be in the same direction as the electric field for the positive charge. So there's going to be a force on the positive charge like this. For the negative charge, it'll be the opposite direction, so there will be a force on the negative charge to the left. Okay. Notice those two forces are equal and opposite because the charges are equal and opposite. So the net force is going to be F plus F minus, which is just 0. So there's no net force on this dipole. But you should notice that there is going to be a torque. The torque will not be 0. The two different parts are going to want to rotate, and the two rotations are going to add together rather than canceling out. All right, so let's figure out about the torque. So I'm going to calculate the torque around the center. Since there's no net force, I expect the center of mass to stay in the center. Although I didn't necessarily tell you what the mass distribution is. So for instance, for the water molecule, the center of mass is not in the center, but that's a detail. So let's say that we calculate the lever arm here. We have R plus the position of the positive charge. And remember, the torque is R cross F. All right, so I'm going to define this direction, theta. So relative to the electric field, there's some direction that this dipole is oriented. Okay, so the torque is going to be the torque on the positive one plus the torque on the negative one. Those are going to add together. Okay, and what that's going to be, since they'll turn out to be the same size, it'll be just 2 of each individual torque, which is going to be the R, or d over 2, times the force, which is QE, because it's an electric force, times sine theta. Okay, and I should make this not a vector, since I just want to calculate the magnitude. Okay, so the 2's cancel, and what we're left with is that the net torque is going to be Q times D times E times sine theta. Okay, so all it depends on is how big those two charges are, and the distance between them, and the electric field, of course, and the orientation. So it's helpful to define a new quantity, P, which is Q times D, where D goes from the negative charge to the positive charge. That just gives us an arrow that represents the direction of the dipole. So in this case, D looks like this. Okay, and P is the electric dipole moment. Okay, so it's essentially how strong is our dipole. If the charges are bigger, the dipole is stronger. If the charges are closer together, then that's going to make the dipole weaker. So a really big dipole would have really big charges that are separated by a lot. Okay. And so using P, we can represent the torque even a little bit more simply. The torque on a dipole is going to be equal to P cross E. Okay, and the result of this is just that the dipole wants to align with the electric field. If the dipole is aligned with the electric field, there's no torque. If it's anti-aligned, there's no torque. If it is 90 degrees, you get the biggest torque possible. Okay. Interestingly, and I'm not going to derive this, there's also some energy associated with twisting the dipole away from the direction it wants to be oriented. So if you imagine a dipole that's aligned with the electric field has the lowest energy, and as you crank it away from the direction of the electric field, it's going to want to snap back into alignment. So you're basically adding energy as if you were stretching a spring. And so the energy that's associated with that alignment, the dipole energy, is equal to negative P dot E. Okay, so the dipole being aligned with the electric field is the lowest energy state. That's the stable state. The dipole being opposite the electric field is the unstable state. It'll want to turn then in order to go back. And so this is actually the way that a microwave oven works. By making electric fields that are rapidly changing, it causes the polar water molecules in your food to oscillate back and forth as they keep trying to align with the field, and that increases their energy and causes the food to heat up. Some foods do this really well, some foods don't, which is why your burrito might have some hot spots and some cold spots. It depends on whether the materials have lots of water or lots of fat or what exactly they are made out of. And in addition, the pattern of the electric fields in your microwave isn't totally uniform either, which is why the plate rotates in the microwave to try to even that out a little bit.